And we come to this concept by first reviewing the basic quantities we're dealing with. So the first one is the mechanical strain. So strain is the basic variable that measures the deformation of the tissue. So if this is your undeformed tissue, you deform it somewhat, then this mechanical strain, defined like that, will measure or quantify how much your tissue is deformed. That's in contrast to the mechanical stress, which is a measure of load. So what's the load acting on your tissue? Again, this is a piece of tissue, and we would have a force acting on this tissue. Then the stress is defined as force divided by area, and how the stress actually acts on this area defines if it's a shear stress, which is in parallel acting to this area, or it's a normal stress, which acts in normal to this area. So we have these two fundamentally different stress measures. Then finally, the third entity in this concept is the constitutive description, which then connects our mechanical stress to a strain to our stress, and this basically defines the constitution of the tissue. If I talk about tissue in the aneurysm case, I mean always the ball tissue, the aneurysm ball, and also the intraluminal thrombus tissue. So this constitutive description is then identified through mechanical testing, so in vitro testing, and you see one of these tests here. That's a piece of intraluminal thrombus tissue, which is cyclically loaded, and then we measure the stress and the strain in order to derive this constitutive description. So now, what is this concept good for? And there we first look to blood flow-induced wall shear stress. So blood is a viscous medium, and the viscous medium is going to develop a kind of a parabolic flow profile if it flows over a wall. And this parabolic profile induces wall shear stress sensed by the endothelial layer here. And it's very well known that the endothelial layer or the endothelial cells respond with different biological cascades with respect to this wall shear stress. So there is very well understood vascular physiology and pathologies related to this wall shear stress measure. Today we're not going to talk a lot about blood flow induced stress. We're going to talk about blood pressure induced stress. And if you pressurize the aorta, like indicated here, then this blood pressure is translated into tensile stress along the circumference direction and tensile stress along the axial direction. And this is a normal stress since it acts normal to the area here and distributes this load through intimate, medial, and adventitial layers. Right, so we're going to focus on these wall stress for our rupture risk assessment. Now, in order to make this concept, this biomechanical concept, applicable in the clinic, it has to be integrated in the clinical workflow. And this is indicated here. It starts with the clinical problem, which is our aneurysm. We're going to build the computational model. This computational model will predict stress, because stress is a quantity you cannot measure. You can only predict stress through simulations. So this model is going to simulate stress distribution all over our aneurysm, and this information will then help to find our clinical intervention criteria. So this is the idea how this biomechanical rupture risk assessment enters the clinical workflow. Of course, most important is this computational model, and the reliability of this model will largely define if this concept is successful or not. Now, what does this mean from an implementation point of view? So what you have to do is you first have to do image reconstruction to build a three-dimensional geometry from your aneurysm. Then you do a finite element calculation in order to predict or simulate ball stress, and then this prediction will generate a vast amount of data, and you have to extract those information that's important to you. So you have a smart tool of data interpretation. And of course everything has to work within a clinical environment, and so far the A4 Clinic software from VASCOPS is the only one who fulfills this criteria. It's CE approved, that means you can use it for clinical decision in Europe. The whole process is done in 10 to 20 minutes. We're going to see that later in the live demonstration. And it can be done by a clinical operator, so it's actually certified that it can be done with a clinical operator who has no whatsoever experience in computation. Right. Now let's summarize that. So we learned that the biomechanical concept is built on these three main ingredients, which is tissue strain, that's a measure of deformation. Tissue stress is a measure of force or load acting within our tissue, and the tissue constitutive model, which defines the constitution or the elasticity of our tissue. Now that's the theoretical part. The implementation is based on image reconstruction, so you have to build a three-dimensional model. It means, of course, that you have to have image data that allows you to build a three-dimensional model. This three-dimensional model is then turned into a finite element simulation, which predicts your stress or risk quantities, and then you have data analysis. Specifically, this biomechanics concept enters the finite element simulation. So in order to perform this finite element simulation, you have to be aware of these quantities up. Right, so that's the theoretical part here, and now let's